Alright, so welcome to day 2 for Unit 1. Today we are talking about GHS symbols, units and measurement, and accuracy versus precision. So we're going to start off by talking about these GHS symbols. So GHS symbols are basically just symbols that go on the containers for chemicals so that, like they're warnings, so that we know what to be aware of about that chemical, either how we need to store it, how we need to dispose of it, or like how we need, like what we need to be aware of when handling it. So we're going to start with this first one, this exclamation mark. This is called an irritant. And so what the irritant tells us is literally it just means that this chemical irritates your skin. The way I remember that the exclamation mark is irritant is because the exclamation mark just looks like an upside down eye. So irritant, exclamation mark, upside down eye, that's how I remember it. The next one that has like what looks like this black bar and a pair of hands, this is corrosive. And this means that it eats away at objects. And the way I remember it, like eats away, corrodes, right? It starts to kind of like go through it. It's a little hard to tell. You definitely can't see it from the video, but if you look at your notes, you might be able to see that it looks like we're starting to kind of like create this divot inside this black bar. That's kind of what tells me like it's eating away, it's corroding, corrosive. Honestly, the others match up fairly well, so if this is the only one you can't remember, well then automatically it goes with corrosive because it's the only one left. Because the next one, the skull and crossbones, this means toxic. And really, toxic just means poisonous. So be very careful when handling it. The next that looks like a flame is flammable. It means that this chemical is easily set on fire. And the last one, it looks like there's a dead tree and like a dead fish. This is environmental systems. Sorry, environmental issues, not systems. That's the class. This is environmental issues. And that just tells us that it's going to be toxic to aquatic life and ecosystems. So it should not be like poured down the sink. It doesn't even go in the trash. We have to dispose of it very carefully and then actually have a chemical disposal company come and pick it up and handle it from there. Alright, so the big thing for this for today is talking about units. So in science, I'm sure you're aware that we use the metric system, which is not what we use in the US. We use the customary system in the US, but in science, we use what pretty much the rest of the world uses, which is the metric system. Another name for that is the SI system. However, the SI system is literally just the metric system. Alright, so there are two categories of units inside the metric system. The first is an SI base unit. This is just the simplest single unit for a measured quantity. So that means it's going to be something like a meter, second, grams, just a single unit. Whereas a derived unit is a unit that comes from multiple other units combined. Some really common examples of this: grams per milliliter, we'll talk about this a lot. But another one is actually this here, centimeters cubed. So you may look at it and go, well, that's just 1 unit. However, this centimeters cubed, really what that means is it's centimeters times centimeters times centimeters. So there's centimeters 3 times. There's actually 3 centimeters in this single unit. So even though it's technically not multiple different units, it's still multiple of the same unit combined. So centimeters cubed would in fact be a derived unit because truly it is multiple units. We're just making it easier for us to write. Okay, so go ahead and flip to the next page. And we're going to talk about these quantities that we're going to commonly encounter and measure in class. So the first one is mass. We measure mass a lot. And whenever we measure mass, what we're actually doing is we're really measuring the amount of matter. So throwback to middle school, matter is what makes up everything here in the universe. Everything is made up of matter. So whenever we're measuring the mass of an object, we're actually measuring how much matter that object has. What we're going to use to measure that? Well, we're going to use a scale or balance, different words for the same thing. The units that are most commonly used to represent mass are kilogram and gram. And the symbols that we use to abbreviate that, kilogram is kg, and gram is just g. All right, so whenever we measure the length of something, what we're doing is truly we're measuring the distance. So we're measuring the distance between points. So for example, if I wanted to determine the length of this sheet of paper across, what I'd be doing is I'd be measuring the distance from this point to this point over here. So I'm just measuring the distance between 2 points to determine the length or width of this piece of paper. Well, how could I do that? What am I going to use? I use a ruler. Could use a meter stick, something like that. However, in class, we're not going to be measuring anything long enough to use a meter stick instead of a ruler. Now, what units? Well, we're going to use meter and centimeter most often to represent length. The symbol for meter is m, and the symbol for centimeter is cm. Time is a little funny to think about because whenever we measure time, whenever we think about time, what are we measuring? Well, we're measuring time, right? But we're not writing down on our lab papers what the time is. We're not saying it's 1:59 p.m. We are measuring how much time this reaction took. So really, we're measuring time elapsed or the duration. I try to avoid writing down how long it took because long is often, can often be confused when talking about length as well. So whenever we talk about measuring time, we're actually measuring time elapsed or the duration. Well, we're going to use a timer, stopwatch. We can even use a clock. When we measure time, we could use the second hand, okay? And speaking of secondhand, the unit that we use for time is seconds. We abbreviate seconds with an S. We're trying to get away from you writing SEC. Now, SEC would not be counted wrong. However, S is faster, and that's what is used in physics, so that's what we use in chemistry. So seconds is the symbol for that is just S. All right, temperature. So temperature is even weirder to think about. So temperature, we say we're measuring, we're measuring how hot it is, heat, okay? However, truly what we're doing is we're measuring the average, so this is average, the average kinetic energy of the molecules that make up the substance. So I like to think of it, so kinetic energy is the energy of movement. So whenever I go for a run, I'm going to have more kinetic energy than when I'm sitting. And whenever I'm on a run, I'm going to feel a lot hotter than I am when I'm just sitting down, not really moving much. So the more kinetic energy, the higher the temperature. What do you use to measure temperature? Well, you use a thermometer to measure the temperature. Now in chemistry, we use two different units when referring to temperature. One, I'm sure you've seen before, Celsius. That's what literally like the rest of the world uses when they measure the temperature outside. They use Celsius. But in chemistry, we're also going to use Kelvin. So Kelvin is actually truly the measurement of kinetic energy. Now on Earth, we can't have anything that has zero kinetic energy. Everything is slightly moving. So the molecules in every substance are just ever so slightly moving, even if they're just barely like vibrating in place. Okay? So we can't have 0 Kelvin. But we can't have 0 Celsius, right? 0 Celsius is freezing. Well, 0 Celsius is actually 273 Kelvin. We'll talk about converting later. You don't have to worry about that right now. But this is why whenever we're in the lab, we use Celsius. Because can you imagine the thermometer that we'd have to use if 0 Celsius is 273 Kelvin? Like, we wouldn't be able to hold that or be able to read it accurately. So instead, we use Celsius to make those numbers easier for us to handle. Now, the symbols for these, Kelvin is a capital K, and Celsius is degree C, capital C. We do not use degree with Kelvin because, again, Kelvin is truly the measurement of kinetic energy. So no degree sign for Kelvin, just for Celsius. All right, volume. Volume is the amount of space an object takes up. So whenever we measure volume, we're measuring the amount of space. Well, how do we do that? If it's a liquid, we can use something like a graduated cylinder, a beaker, anything like that would work. But maybe, let's say we've got a cube in front of us, and we don't have to get out a graduated cylinder and use water to measure that. You can, but an easier thing might be to use a ruler and just measure the 3 sides and multiply them. So you could use a graduated cylinder, a ruler. I'm going to put ETC for etc. to say, like, you could use a beaker or a flask or something like that as well, even a meter stick. All right, so whenever we're talking about units, whenever we refer to liquids, we really use liter and milliliter. The symbols for those are L, capital L, and then milliliter is ml, lowercase m, uppercase L. When referring to solids, we're way more likely to use meters cubed or centimeters cubed. And that looks like this. Okay, so the last measurement we're going to talk about is density. Density is actually a combination of 2 of these measurements, 2 of these quantities that we already talked about, mass and volume. So density, to calculate density, we actually take mass divided by volume. So whenever we think about how to explain density, what is it measuring? Well, we're measuring mass and volume. So really, we are measuring the amount of matter in a given space. Another way to think of it is compactness, or how close the molecules are to each other. The closer they are, the more dense, because we can fit more matter in that same amount of space. Okay, well, how can we measure density? Well, we have to calculate it, right? We need mass and volume. So we have to use the equipment that we would need to measure mass and volume. So to measure mass, we would need a scale. To measure volume, we might need a graduated cylinder. or a ruler. Then I'm going to put etc. again, because you could use whatever you need to measure the volume of that object. The units that we use are going to be either gram per milliliter, so G/ml, or gram per centimeter cubed, G/cm cubed. All right. So these are all of the common measurements that we're going to discuss and possibly use in the lab this year. Okay, so speaking of these measurements, in order to take these measurements, we need to know how to read equipment. Okay, so on your sheets, you might not be able to tell, and it's probably not showing up well on the screen, but this right here is supposed to be a test tube. Okay, so if you've got what looks like a blank space right there, draw in a test tube. And we're going to go through and label these just to test our equipment knowledge. This is a beaker. This is a graduated cylinder. This, like I said before, is a test tube. And this last one is an Erlenmeyer flask. Okay, so I want to know which of these pieces of glassware is going to be the most precise and which is going to be the least precise. So if we were to take a look at all of these, what do you think is going to help us be the most precise when trying to figure out the volume of a liquid? Well, the most precise is going to be the graduated cylinder because it has the most tick marks. It's got the most markings. So that means we're going to be able to read it more precisely because we're going to be able to estimate better. Whereas if we take a look at this beaker, these are measured out at 50. So actually, they're measured out at 25, right? So we're not going to be, every 25 in between there, it's going to be harder to guess. Whereas these look like they're measured out at 0.1. So we're going to be way more precise using the graduated cylinder because it has a lot more of those tick marks to let us measure. Okay, well, the least precise is going to be this test tube because it doesn't have any markings for us to measure. In fact, test tubes we don't use to measure the volume of things. We pour already determined volumes into test tubes. Okay, so if you're given something else, how do you know if something's the most precise, the least precise? Well, the most precise is going to have the most markings. Whereas the least precise is going to have the least amount of markings. Okay, so on the next page, we're going to talk about actually recording them and reading. So when recording and reading equipment, we always report all of our known digits plus one estimated digit, and we can't forget units. Okay, so what does it mean by known and estimated? So looking at this ruler here, looking at A, well, A, if I were to try and figure out how long A is, where it is on this ruler, what I know is that I know it is past the 0.5 marking, but it is not at the 0.6 marking yet, which means I know for a fact that A is 0.5 something. So I'm going to go ahead and put 0.5 because I know A is at least 0.5. I know that for certain. Now I can look and say, okay, well, I can estimate how far it is between 0.5 and 0.6. Well, this looks a lot closer to 0.5. I'm going to go ahead and say maybe this might be 0.52 centimeters. And that 2 is my estimated digit. So once I don't know for certain, that's the number I stop with. The way that you figure out where you stop, I like to use my tick marks. So each of these markings is worth 0.1. So that means I'm going to know for certain whatever is in the 0.1's place, the 10th place. I'm always going to know for certain the 10th place when reading this ruler, which means my estimated digit is going to be in the 100th place. So I'm always, when reading this ruler, going to have 2 numbers after the decimal. All right. Looking at C, I'm going to skip B. You can do that on your own if you'd like. But looking at C, I know that C is past the 1.5 marking. So I know for certain C is at least 1.5, but it hasn't reached that 0.6 mark yet. I might say this is 1.58 centimeters. Not forgetting the centimeters, because I need to make sure that this is centimeters and not maybe, you know, baby elephants. Okay? That'd be really kind of disturbing to have 1.58 baby elephants hanging around. I don't want half of a baby elephant. Okay? So, I need to make sure that I'm putting my unit. Last one on here I want to do with y'all is D. So looking at D, to me, D looks like it is exactly on this 2.5 marking. It looks exactly on this 2.5, so I'm going to say it is 2.5. However, I know 2.5. I can't say with certainty that it isn't 2.51. But to me, it looks like it's exactly on that 2.5, but I can't just leave it at 2.5 because that's my 10th place. I have to have 2 numbers after the decimal here. So how do I keep it at 2.5 that have 2 numbers after the decimal? Well, I can say it's 2.50 centimeters. So if something looks exactly on the line, just add a 0 after it. All right, so I was talking about how you need, like, you know that you need 2 numbers after the decimal here because each of these values, these tick marks, is 0.1. So I have to estimate, right? Well, that's talking and referring about precision limitation. So precision limitation is the last digit you report. Really what that means is I'm going to know what the place value is of that digit you're reporting. Okay, whenever you're dealing with glassware and rulers, it is your estimated digit. Reminder, your estimated digit is 1 past the known, or our tick marks. So whatever place value our estimated digit is in, that's your precision limitation. So like this ruler up here. Our last digit we wrote, our estimated digit, is in the 100th place. So the precision limitation of our ruler is the hundredths. Because that's where my estimated digit is. Okay. Whenever we're dealing with something electronic, it's a little different because we can't properly guess, right? So looking at this right here, this scale, it says 0.0. We can't say with certainty it's not 0.01 or 0.05. We don't know if there's a speck of dust or something on there that would cause it to be a little more than 0.0 exactly. But we have no way of telling, like, of making a guess. So we don't. So for electronic things like our scales, the precision limitation is the place value of the last digit shown on the screen. All right, looking at this graduated cylinder here. This graduated cylinder, reminder, whenever we read graduated cylinders, we look at the meniscus. The meniscus is our curve, and we read from the very bottom of our curve. We do not read from over here, the highest point. We read from the lowest point of our curve. So here, so this is 30, and this is 40, meaning this is going to be 35. So I can say with certainty that the volume of this is more than 36, but not 37. So I can say with certainty it's 36 something. But that's with certainty, so I have to estimate something. So I'm going to say 36 point, and to me it looks a little, maybe a little more than halfway. So I might say 36.6 milliliters. This 0.6 is my estimated digit. That's what I guessed, okay? Which means the precision limitation is the tenths place. That's the place value of my last digit that I wrote. Looking at the scale, this scale reads 0.0 grams. It is electronic. So what we report is exactly what's on screen, 0.0 grams. Nothing else. The precision limitation of this one would also be the tenths, because the last thing I wrote was in the tenths place. All right, so we are almost done. We are going to finish by talking about accuracy versus precision. So accuracy and precision are things that we use to analyze our data. Accuracy is how close a measured value is to an accepted value. So really, how close is your value to what we know to be true, what it should be? If we know a pencil is 19.0 centimeters long, how close did you get to that measurement when you measured it yourself? That's accuracy. Precision is how close your measurements are to one another. So let's say you had that pencil and you measured it multiple times, okay? Well, how close were each of your measurements to each other? I don't care how close they are to that 19.0, I care how close they are to each other. Okay, one thing that makes it kind of easy, like it's easy to visualize using these like bullseyes, okay? So if I were to throw a dart, or throw multiple darts, okay, and I managed to be both precise and accurate, that means, so precise means that all of my throws were really close together. Accurate would mean that I hit them like at the bullseye. So it might look something like this. All of my throws were grouped really close together and they landed in the bullseye. Grouped close is precise, in the bullseye is accurate. If I managed to be precise but not accurate, that would mean that my throws were all kind of like in the same spot, but they weren't anywhere close to the bullseye. So I might have managed to throw them like over here. They're all really close together, but they're not anywhere close to my bullseye, so I wasn't accurate. Okay? What if I threw these and I wasn't precise or accurate? That's what I would do in real life, let's be honest. I am not a dart thrower. I have horrible hand-eye coordination. So if I wasn't precise or accurate, my throws would probably be all over the board, okay? I might get lucky and end up in the bullseye once, but like they're all over the place. I wasn't precise, and on average I was not accurate. The last one, what if I was accurate but I wasn't precise? So what if I managed to get in or close to the bullseye, but they weren't grouped well together? So maybe that means I hit the bullseye, and And then I hit really close to the bullseye, but I hit like top, bottom, left, and right. I wouldn't say that I was very precise. They weren't super well grouped together, but I was really close to the bullseye each time. So this is a nice visual, but we're in chemistry. We're not playing with darts and bullseyes in class. Instead of using these, what we really use accuracy and precision for are data sets. So looking at this table here, we have 4 students, students A, B, C, and D, and they had a sample, and its mass is known to be 2.43 grams. Okay, so each student measured it 4 times, and they got the following data. So let's take a look and figure out who was accurate, precise, both, or neither. Okay, so looking at student A had 2.29, 2.63, 2.13, and 2.92. None of those were particularly close to 2.43, so they weren't accurate. And these were not grouped close together. They were all in full range in the 2s, so they were not precise. They were neither. Looking at student B had 2.76, 2.76, 2.77, and 2.75. Those were grouped really close together. The furthest apart 2 of them were 0.02, these 2 right here. So I'd say they were really precise. However, were they close to 2.43? No, they weren't. So they couldn't be accurate. So really, they are just precise. Looking at student C got 2.43, 2.42, 2.43, and 2.44. They're all grouped really close together. Again, the farthest 2 of them are from each other are 0.02 grams. That's really small. That is for sure precise. And let's take a look. All of these were really, really close to 2.43 grams. So I'd say they were accurate as well, which means they were both. Looking at this last one, student D, they only took 1 measurement. That measurement was exactly correct. It was 2.43, but we don't have any other trials to compare it to. So we can say that student D was accurate, but without having any other measurements for comparison, we can't say if they were precise or not. So student D is just accurate. Now, another way just accurate might look is if we took the average of all of the numbers and it came out to really close to 2.43, but they weren't close to each other. So if you're looking at the numbers and you can't tell just by looking that these numbers were close to 2.43, what you would really need to do is take the average to determine if they were accurate or not. Alright, so that is day 2. If you have any questions, please come see any of us during our tutorial times. They are, again, linked on Canvas, posted outside our doors, in our rooms. They are there. So please come see us if you have questions. I hope you have a great rest of your day. Bye.